going to call this family C. Absolutely not.
No.
Any substance of the numbers will be this.
Yes. Now it's saying that a set is computably enumerable is okay. There are some equivalent statements to it, but yeah, we will just receive information that these elements are part of the set. Then we'll receive later information. Well, all the ones I told you before are part of the set, and these 12 others are part of the set. And each time we see one of those, we're supposed to guess an index, and we're supposed to guess the same index almost all the time. And it's supposed to be right. So he had a name for this and a name for each of the other variations. There are all kinds of different convergence criteria you can put on this. You can also allow that you're getting both positive and negative information about the set. These 12 elements are in, but these 5 are not in. There are several variations you can make in this definition, and Gold made lots of them, and others have made others since. This particular one he called learning from text by example. And his idea was that this modeled the process of learning a language. And in his first paper on it, he even cross-referenced some psychological research about how children learn natural languages. And he had what he took as some evidence that, well, when you learn a language, you're learning the rule, the algorithm that will enable you to produce all of the grammatically acceptable sentences of that language. And then people have done a lot of other things with this. More recently, you can fix a ring. Maybe polynomial ring, maybe coordinate ring of some variety or something. Fix a ring, and then you have its family of ideals. Maybe just the computably enumerable ideals or something. Finitely generated ideals would do nicely. And so somebody gives you a few elements at a time of the ideal, and you try to learn which ideal you're in. You start with some fixed vector space, and then you're trying to learn some subspace of that. That's another problem. Both of these have been worked on, certainly within the last 20 years by fairly serious people doing serious new work where they had to know new things about computation to figure it out. And usually, with things like these, usually there's some nice algebraic characterization, like you can do this if the ring is Noetherian. I don't know if that's a theorem, but it's a condition like that. It's some condition you would recognize. Now, from this problem, there arises another one. And it's related to this thing I was saying about there being some nice algebraic characterization for when you can learn it, when you can't. The problem is this. I have some family of sets here. I'd like to know whether this is possible for that family. whether the learner has a winning strategy in the game occasioned by this family of sets. I'd like to distinguish where you can learn it, where you can't. This is hard. In particular, it is too weak a criterion to say that it's so hard that a computer couldn't actually do it. To say that it's not computable to decide, that's too weak. Fortunately, computability theorists, some people would even say the essence of the subject is to define and calibrate and prove things about different criteria for what's hard and how hard things are. So I'm about to define sigma 0 in and pi 0 in, but the base case is sigma 0, 1, which is the computably enumerable sets. Equivalent to saying that it's computably enumerable is saying there is some input you could give the computable function that would produce that output. Now there are definitely computably enumerable things, existentially defined things. There are definitely things like this that are not computable. Some of you have heard me talk before about the Microsoft Windows problem. If you are running a machine with Microsoft Windows, less now than in the old days, but it is still true to some extent, your computer someday may jam up. And you sit there thinking, is it just running slow? Or is it really, really crashed this time? And so you wait a few minutes. Nothing happens. Well, should I wait a minute more, or should I just give up now? And there's no way to get good information that there's not going to be an X somewhere down the line. So this includes some non-computable sets. So the complement of a set like this is a pi 0, 1 set, where the thing you're waiting for isn't the example. You aren't waiting for the example to show that it's true. You're waiting for the counterexample to show that it's false. There we go. So you go up a step in this hierarchy by adding on another quantifier. Really adding on another alternation of quantifiers. And there are, for essentially the same reason as you can find sigma 1 things that are not computable. You can find things at each level that are new at that level.
Blue screen belongs to which level?
Well, if you see the blue screen, then you actually have evidence that it's stopped.
That's right.
Say sigma 0, 4, didn't it? Yep, sigma 0, 4. So this little word complete here I haven't defined. I may say something about it later, but essentially it means as hard as it could possibly be and still be of class sigma 0, 4. As hard as it could be and still only need 4 alternation of quantifiers to define it. So this was a nice result. It tells you exactly how hard it is, if you're looking at a class, how hard it is to say whether it's learnable or not. And in the scheme of things, sigma 0, 4 is not that bad. Checking isomorphism of vector spaces is pi 0, 3. So it's not much harder than checking whether 2 vector spaces are isomorphic.
Pi 0 or sigma 0?
Pi 0, 3 for distinguishing vector spaces. So it's a whole lot more like checking whether vector spaces are isomorphic than checking whether countable groups are isomorphic. Those are not in any of these classes. Go through all the n's, all the sigma n's and pi n's, make this transfinite, go through all of those, you still don't have isomorphism of countable groups. So this model of learning has something about it that practical people do not love. By practical people, I mean, for instance, Amazon. Because Amazon keeps track, you know. They have in mind what books you bought from them in the past. And they may even have your ratings on some of them. And they know which web pages you've looked at and all this. And what they really want to know is, what product can I put in front of this customer that they will like and buy? And they've gathered some data from you. And they have a general clue that these points all resulted in selling you something. These points all resulted in not selling you something. What they'd like to learn is the boundary between these sets. But their standards are not these standards. For instance, they are perfectly okay with it if their algorithm is only right 80% of the time. Their algorithm's right 80% of the time, they're jumping up and down celebrating. They're happy with it being wrong a little bit. It shouldn't be wrong all the time, it shouldn't be worthless, but it's okay if it has some probability of error. And also, it's okay if it's okay especially if it misses on the close calls. So there's another definition of learning that takes those into account. So X is the instance space. It underlies everything. C is playing a similar role here. It's a subset of X. A subset of X is what we're trying to learn. And C is a collection of subsets of X. We call it a concept class. Okay, I'm not done yet with the definition, but the algorithm can't care what the probability distribution is on X. Points are going to be drawn from X according to some distribution. They're going to be drawn from there, and we'll tell the machine, yep, this one's in, that one's out, that one's out, that one's out, this one's in. We'll give the machine that kind of data. It gets to say how many points it wants to look at. So there are two kinds of probability in here at the end. First level is that it can be wrong by a measure epsilon, so it can be off by a little bit, measured according to the same distribution that it got its data from. And it can be even more wrong than that, except that it shouldn't be more wrong than that too often. That's where the acronym comes from. Probably approximately correct. So this was a definition in mid-80s, I think, from Valiant, who is unapologetically a computer scientist. So here's a different definition for learning. And you can't ask the same question for that, and that is the question that I'm getting to, the question that I actually know the answer to. But to get the feel of it, I should give you at least one example of this. So we're looking at linear half spaces of the plane. A couple of you have seen this picture before.
It's cross.
I expect many of you have seen that picture before, but the picture I'm about to draw. So you get some data that says these are in, this one's in. And remember, the thing actually is a linear half space. So the points that are in have to all be in the same linear half space that doesn't include any of the points that are out. So what you want is to be able to draw a line here, where all the green points are on one side and all the orange points are on the other. This is particularly ideal data, but remember, it comes from assuming that we have a linear half space to start with. And it's okay. It's okay if instead of learning this one, we learn this one. It's okay if they're off by just a little bit. And it may happen sometime, if we're drawing these points at random, that all the points we draw are green. We'd have to get fantastically unlucky with our random data to get that. But it could happen. And it's okay in that case if we're just thoroughly wrong, because we have no idea where to draw the boundary. It's okay to be thoroughly wrong then.
You could still draw a whole family of possible lines around it, right?
Right, but our rule is we have to come up with one line.
Wesley, I have a question.
Okay.
So, this problem is looked at a lot in statistics. It's
Yeah.
a statistical discrimination problem.
Mm-hmm.
So you have like the kinds of populations where you have a sample from and how to draw the line.
Yeah.
So now, of course, because it's coming from a sample, you're making some mistakes. You can make some mistakes. So how to minimize the probability of misclassification, right?
Yeah.
So based on that, you can find the optimum line.
Mm-hmm.
So
And
is this? I'm trying to find out where is that matching or differing.
Well, so I think what the things you're describing are the algorithms.
Right.
So if you know actually, given some data, how to draw a good line here, then you have a solution to this problem. And in fact, the class of linear half spaces of Rn for any n actually, the class of linear half spaces is PAC learnable. And that body of knowledge that you're talking about is a very elaborate proof that it's PAC learnable. You can prove it with something much more modest than that if all you're trying to do is prove that this class is learnable. But yes, that's the algorithm. You can do the same thing, of course, with, and this may be what Eric was talking about, with n-gons. If you say you want to fill in quadrilaterals, if you're trying to learn a quadrilateral, okay, you'll get some points that are in, you'll get some points that are out. And, well, for an n-gon, you have to learn n lines. Let's see, do I want to talk about that? I don't think so, actually. Let me come back to it. There is an alternate characterization of this definition of learnability in terms of something called the I'm forgetting the name of the guy. The VC dimension. People always call it by the initials. Vapnik-Cherevonenkis dimension. There is a characterization in terms of that is heavily used in my proof. But giving all of the gory details of a proof is not always the ideal thing for a talk like this. So I may not go into all those details. So, what I'd like to prove is a theorem like this. Now, to prove a theorem like this, being sigma 0, 4, or whatever level, has to make some sense. You remember when I told you we were only talking about subsets of the natural numbers? Well, remember when I told you there was going to be some excitement about that later on? There is a way to deal with this. In fact, there are a lot of ways to deal with this. And they all seem to be good for different things. I'll show you one that seems to be good for this kind of thing. The is should be in quotation marks here. But you start maybe at 0. Is it greater than 0 or less than 0? And then for this one, is it greater or less than 1? This one is it greater or less than 1/2? This one, is it greater or less than 2? You can keep expanding this. You wind up, okay, you can play the same game with the unit interval instead of the reals, and there, what you get looks exactly like the binary expansion of the number. If you're playing it with the reals, okay, it has to look a little bit weirder because the reals keep going out as far as you want. But you can play the same game, making it the set of paths through a binary tree. You can even do this with a little more difficulty. You can even do it with Rn. You have to think some about how to deal with many coordinates, but you actually can code that into this tree. For instance, if n is 3, this one will tell you about the first coordinate, this one will tell you about the second coordinate, this one will tell you about the third coordinate, then the next 3 will tell you the next digit of the first, second, and third coordinates. I'm going to make sure that I wrote this the same way. By the way, I called an infinite binary tree 2 to the omega. So these are equivalent conditions. First, so this condition, okay, it does call on you to believe that a subset of this can be computable. But what I mean by that is, if you take some finite string, you should have an algorithm that looks at that string and says, is it in or out? You can do that. The finite strings in here form a countable set. You can talk intelligently about them. And note that the full set of reals satisfies this condition. A linear half space satisfies this condition. Think, for instance, of n equals 1. A linear half space is either greater than x or less than x. So at some point, you chop off that part. Everything that would give you something greater is in the tree. Everything that would give you something less is out of the tree. So linear half spaces satisfy this criterion. second criterion is that you can check whether a string is in C by looking at that string and seeing whether it satisfies some pi1 condition, some condition defined by a single universal quantifier. In these cases, we say that C is a pi01 class. No relation whatever to concept classes. It is an unfortunate clash of terminology. Unfortunately, both of these are very, very, very well-rooted terminologies in their respective places. There is no chance of changing either one and having anybody know what I'm talking about. So, a set like this is a pi01 class. And these pi01 classes are very well studied. In some respects, they act a lot like computably enumerable sets do. A pi01 class of reals is not unlike a computably enumerable subset of the naturals. And when I say not unlike, I mean to say that there are certain orderings that you can put on them, certain lattice structures and things where those structures look similar for the two families. Find pi01 classes. Notice that linear half spaces are pi01 classes. Other examples of pi01 classes. If you start with a graph, to make it interesting, it should be an infinite graph. If you take an infinite graph and you want to color it, you want to color the vertices so that adjacent vertices have different colors. So you start making decisions. Every branch point in the tree is a decision. You color this one blue. You color this one red. You color this one blue. It's adjacent to this one after all. But wait a minute, these two are adjacent. Okay, scrap that branch. We won't extend that one any further, so we won't get a path through there. We start off on some other, and we never get stuck, so that one makes a path. So the set of K colorings is one of these things. And you can even write down what it means to be a coloring in terms of a universal quantifier. For all x and y, if x and y are adjacent, they have different colors, something like that. Use consistent notation here with my notes rather than what I've written here. So take a subset of the infinite binary tree, which could just as well be the reals if you like thinking about reals. And since I'm going to be talking about the metric structure on them, you probably do like thinking about the reals. tell you in a minute what this function's supposed to do, but it takes in a finite string and a rational number. What it's supposed to do if sigma is within R of something in set S, then we should say 1. If sigma is so far away from S that you can go out by 2R and not meet S, then we should say 0. And we should always say 1 or 0. We should always try to guess at the answer. This is actually not unlike what a digital camera tries to do. It sees a continuous image and tries to render it into pixels. It has to decide, should this particular pixel be turned on or off? And, well, if it's really close, no problem. If it's clearly in an illuminated area on the frame, you should turn it on. If it's clearly out of an illuminated area, you should turn it off. Now we get back into the learning. An effective concept class Okay, so the concept classes, you have to have a list of all the sets that are fair. You have to have a list of all the things in the concept class, all the things like listing all the linear half spaces. There's a slight problem with that you can reduce it to a countable set of them by density arguments. You can think only about, say, the rationally defined planes cutting them. So you should have a nice list of all of them, and all of them should be pi01 classes, and all of those pi01 classes should be something computable. This computable condition roughly says that you shouldn't have so much fine detail in it that you can't figure out the small scale structure. You should always be able to zoom in close enough that you can understand it. And linear half spaces, for instance, that's really not a problem, because they're pretty simple. No matter where you look at them, their small scale structure is very simple. Now for the theorem. Make sure that I actually get it right. So checking whether something's learnable in this sense is pi 0, 3 complete. Complete, remember, means it's as hard as you can be and still be pi 0, 3. Pi 0, 3 means that you can check whether it's learnable or not by looking at a statement with 3 alternations of quantifiers in it. So you can put a nice ordering on these, which I won't define here, but it's a well-known ordering, where one class being greater than another means that the greater one is harder to learn than the lower one. Now, a lot of the degree structures that we have in computability theory, this ordering has a density property. Find one here, find one greater than it. There's one strictly in between, like the rationals are. This one, we don't know. It would, for instance, be a nice thesis project for somebody. Remember when I told you that the program could run as long as it wanted, and we don't even care if you're alive at the end of it? Well, computer scientists are very strange people in some respects. They actually do care if they're alive at the end of it. And so they track time complexity. And they care how much money they have to put into buying more memory for the darn thing. So they track space complexity. And there's some related work on complexity theory around this, but it doesn't take in anything like the range of concept classes that you can pick up with this definition of effective concept class. Whenever they've talked about problems like the question of how hard it is to tell whether something's learnable or not, with this PAC learnability, all the work on that so far is working with little bitty finite classes drawn from finite instance spaces, and those don't actually match what people would like to be thinking about, which are these subsets of Rn and conjunctive normal form formulas, things like that, these infinite spaces. You actually do seem to need this kind of machinery to talk about them. And so there's complexity theory to be done here too. Are there any questions?
So for any set, countably say, or well-defined set, you can attach its class, right? Is there somewhere like a repository of the things which are already known and like open questions?
Things which are known to be learnable or
Learnable or of particular class, sigma, pi.
Yes, so in one case you have the entire literature of the machine learning community, which is enormous. There is a book, and I can get you a reference on it. There is a book that is the standard exposition on PAC learnability that gives some start on that, and then there's an enormous literature later than that. as far as which things are sigma 0 whatever, pi 0 whatever. That's the entire literature of computability theory. If you look down all of my papers, probably about half of them have proved that something new is or is not in one or more of these classes. And it's more or less the same for most people in computability theory. There are several excellent books on that subject and an enormous literature coming out of that. But what's in which level of the arithmetic hierarchy is an entire industry. Actually, it's several entire industries. Other stuff.
Let's thank our speaker.
Yeah, thank you.